So we're going to continue this video right where we left off in the last one. We're going to continue working on systems of equations, working on two different types of problems. One is infinitely many solutions, and then another are systems with no solutions. We're going to start off with the systems with no solutions. In these type of systems, we can call them inconsistent systems. They have no solution. I'm just going to write our example here. So 2x plus y plus 2z equals 29, and then 3y plus z equals 16, and then 2x plus y plus 2z equals 20. So we've got equation 1, 2, and 3. So right off the bat, if we looked at equation 1 and 3, they have the same variables and coefficients on the left side, but different numbers on the right. So if we subtracted equation 1 minus equation 3 and replace it in equation 3, write that out here. If we subtract, so we'll change the signs, we're left with 0 equals to 9. So we're just going to write out our system to show the step here, what's going on. I'll just write it. 2x plus y plus 2z equals 29. 3y plus z equals 16. Now we're left with 0 equals to 9. So these are our three equations, and we see that 0 equals to 9. 0, in fact, does not equal to 9. Because of this, our systems are inconsistent. That doesn't make sense. There is no solution. Now we're going to go into a problem with infinitely many solutions. So it's going to be kind of similar. I'll just write different variables here. So x1 plus x2 plus x3 equals to 12. 2x2 plus 3x3 equals to 15. And x1 plus x2 plus x3 equals to 12. So this is very similar. We have three equations. And I just use these examples to kind of simplify. But if you look at equation 1 and 3 again, x1 plus x2 plus x3, and the coefficients of 1 for all three variables are the same. And this time, their values are equal. So if we subtracted equation 1 minus equation 3 and replaced it into equation 3, because we know they're equal, and if we subtract something that's equal, they're going to be 0. So I'm just going to rewrite our new system of x1 plus x2 plus x3 equals to 12. 2x2 plus 3x3 equals to 15. And then our third equation is basically gone. So if you notice, we have two equations, but we have three variables. So in an earlier video, if we have more variables than equations, we have to represent parametrically. Meaning we have to add a parameter or add a variable, because one of these variables can be any number, theoretically. So we have our equations. I like to start with the least amount of variables if possible. So I'm going to start with this equation, equation 2. I'm just going to rewrite that. 2x2 plus 3x3 equals 15. So I'm just going to solve. I could solve for x3, for x2, doesn't matter. I'm going to solve for x2 in this case. So I'm going to subtract the 3x3 from both sides. So I get 2x2 equals 15 minus 3 times x3. I'm going to call x3 is equal to t. x3 could be any number, it doesn't matter. So when I do that, I end up getting 2x2 equals 15 minus 3t. I'm going to divide by 2 so I can get x2 equals 15 over 2 minus 3 over 2t. So now I have defined x3, I defined x2. So now what's left is to define x1 using our other equation. I'm going to rewrite it, x1 plus x2 plus x3 equals to 12. I'll just plug everything in now. So you could either solve for x1 or plug everything in. Actually, we'll solve for x1. This looks easier. So x1 equals 12 minus x2 minus x3. Now we have to substitute and add our parameters in. We want to write this in terms of t. So x1 equals to 12 minus 15 over 2 plus 3 over 2t, and then minus t. So I'm going to simplify, and I have a fraction over 2. So I'm going to have to say x1 is equal to 24 over 2 minus 15 over 2 plus 3 over 2 minus 2 over 2. So when I do this, I get x1 is equal to 9 over 2, oh, don't forget my t, plus t, 1/2 t. So I have my three solutions here. x1 is equal to 9 over 2 plus 1/2 t, x2 equals to 15 over 2 minus 3/2 t, and x3 is equal to t. So I have all these variables. I needed to introduce a parameter, t, so that we can define all three variables.